So welcome to the second class of electrostatic potential and capacitance. So in this class we are discussing about the potential due to a dipole. The previous class we discussed about what is potential and what is potential energy. Here we are going to discuss a potential at a point. So consider the figure. Here a dipole is there, minus q, plus q, and this is a point P. This is not an axial point, not an equatorial point. So you can simply say that it is at an angle theta from the center, at a distance r from the center, and we can assume two distances, minus q to P as r1 and minus plus q to P as r2. And when you draw a normal here, we can say that this small distance will be r1 minus r2. So here the angle is theta, and here also the angle can be, this is also theta. Okay. Now, for deriving the expression for the total potential, we need to just add the potential due to minus q and potential due to plus q. So V is equal to V1 plus V2. V1 is the potential due to minus charge and V2 is the potential due to plus charge. And V is equal to 1 by 4 pi epsilon 0 minus q by R1. Remember one thing, when you are writing an equation for potential, if it is a negative charge, the potential is negative. If it is a positive charge, then the potential is positive. So 1 by 4 pi epsilon 0 minus q by R1 plus 1 by 4 pi epsilon 0 q by R2. 1 by 4 pi q by 4 pi epsilon 0 taken as common, 1 by R2 minus 1 by R1. Cross multiplying, we get R1 minus R2 divided by R1 R2. Now we are actually approximating something. This distance is R1 minus R2, and from this is a right angle triangle. You can see that. Right angle triangle, you can say that this distance is 2a and this distance is actually 2a cos theta. When you considering this angle, this is 2a cos theta. And also R1 and R2, we can approximate. This angle is small, so R1 and R2 both can be equal to, you can say that R1 is an angle which is nearly equal to R2, which is nearly equal to this distance R. So that is actually an approximation. So, and also R1 minus R2, we can write it as 2a cos theta. On substituting these values here, we get V is equal to q by 4 pi epsilon 0 into 2a cos theta divided by R square. So what is this 2a into q? That is a dipole moment. So rewriting the equation, 1 by 4 pi epsilon 0 p cos theta divided by R square. So this is the potential due to a dipole. And if theta is equal to 0 degree, we can say that this point is at axial line. Then the potential become V is equal to 1 by 4 pi epsilon 0 p by R square. If theta is equal to 90 degree, V is equal to cos 90 is 0. So this is the potential due to a general point. Now the next topic is relation between electric field and potential. For understanding the relation between electric field and potential, we are considering this figure. In this figure, this is a source charge which produces an electric field which is radially outward. I am taking the positive charge. Therefore, the electric field are radially outward. And assuming 2 points A and B in the electric field, and we know that this is Q0 is a test charge. Bringing a test charge from infinity to A, the potential is V. Bringing Q0 from infinity to B is another potential V plus dV. So there will be a small difference in this potential V plus dV, and this is V. and this distance between A and B is taken as dr. So dV and dr are small values. So we know that there will be an electrostatic force acting on this electric field. So we need to apply that electrostatic force is actually away from this charge. Q0 will feel a repulsive force from this capital Q. So normally it moves in that direction. So we want to just apply a force and bring this Q0 from A to B. So the direction of force is actually negative, or if you are calculating the work done, so work done to move Q0 from A to B, that can be written as W is equal to F dot dr. So work is a dot product. So when you are removing the dot product, you can see that F dr cos theta. The angle between F and dr is different because F is in this direction and dr is in opposite direction. Therefore, W is equal to minus F into dr. What is F? There will be a force acting on this Q0, which is given by minus Q0 into electric field into dr. So this is the work done. It can be equal to the equation number 1. Now, in the next thing we are going to discuss, we know that the work done is related to the potential difference. So the same work done can be related. This work done is equal to charge into potential difference. So charge is Q0. What is the potential difference? V plus dV minus V into dV. So this is simply the potential difference. So when you are comparing these two, this is taken as equation number 2. When you are comparing these two, we can say that Q0 into dV is equal to minus Q0 E into dr. Q0 cancel, and E is equal to minus dV by dr. So we can say that electric field is actually the negative gradient of potential. So that's all for today. We will see you in the next class. Thank you.